Good evening. So Professor Kamien will continue his talk on minimal surfaces in Diblock copolymers and geometric scaffolds in material science. Over to you, Professor Kamien.
Okay, hold on. Okay. All right, good morning, or good evening. Is it cold there? I'm
No,
wondering
not
what the
at
weather
all.
is.
No, it's not cold here.
What's the weather?
Weather is very pleasant.
Okay.
Is it cold there?
No, it's pleasant here too. Just wondering. Wondering what I'm missing. So,
Excuse me. Can you
yes,
make full screen?
me like this?
Yes, yes, perfect. Thanks.
Okay. So, last time or yesterday, right, I was telling you about using a scaffold, which is a minimal surface, to to use it as a platform for knitting. And let me just give you a rough idea of how this would be useful for anything. You see, what you can imagine doing is you could imagine having your surface, this gray surface here, and you can imagine having your surface, which has little holes and has the yarn in it. And you can imagine taking the surface and distorting it, right? You could twist it or bend it or do whatever you want. And I could do that just by taking this surface here and doing a diffeomorphism, right? So this is just a diffeomorphism of the space. And then you say, so what? Why is that interesting? Because what I can do is I can then, on the diffeomorph surface, I can now calculate the new paths of the loops. So here I was using paths that were based on following the shape of the surface. Now I have a new surface. And so I could calculate, for instance, I could calculate the arc length or the total curvature if I wanted to. And from that, I could get some sort of energy functional. So I could say that bending the surface costs a certain amount of energy based on the yarn itself. So this is a technique that on which we're working, which would allow us to talk about deformations of a surface and then calculate an energy associated with it. So again, remember I showed you that spring. Let's see if I can find the spring, a cool spring. There was the last slide. Remember I showed you this spring where this spring was completely constructed. This spring constant, this retraction, depended entirely on the way that the yarn was put together. It had nothing to do with the properties of the yarn. So if you wanted to design something and calculate the energy of this, or design some mechanical device that was based on knitting, that'd be great. And I showed you how these knitting machines are cool because they're already current technology. No one has to invent them. And all they do is they take spools of yarn and turn them into 3D structures. So one of our goals is to model these 3D structures. So let me show you. Here are different patterns of knit and purl, like so. So you have red as knit and blue as purl. And all we did here is we said, oh, the red and the blue are regions. All the regions like to have Gaussian curvature. And the regions want to have Gaussian curvature, I'll remind you, because you have one strand like this in front, and you have the other strand in back, like so. And so the surface wants to bend. The surface has one kind of bending moment. Surface is in between, like so. Here's the surface. And so it wants to bend in one direction on one side and bend in the other direction on the other side. The only difference is that when you have knit, it wants to bend this way and this way. And when you have purl, purl wants to do it exactly the opposite way, or 90 degrees, a 90-degree rotation. Like so. So you can either say it's a 90-degree rotation or it's a change of sign, right? So the curvature tensor in one case would be 0 a minus, sorry, it'd be a 0 0 minus a, and the other case it would be minus a 0 0 a. All right, so this would be, you could say this would be knit. This would be purl. And I direct you to a paper that we just put on the archive with Lauren Yu, where we actually show that for a very, very large class of different knit patterns, this very simple procedure works. And so this really demonstrates that the patterns that you get, the three-dimensional patterns from knitting, are really coming from the topology of the scaffold and not coming from the behavior of the yarn itself. So that's kind of a neat application, at least in my mind. It's an application of using these minimal surfaces, then using these tools that I talked about yesterday, where you take surfaces, minimal surfaces, and you build them out of smaller minimal surfaces, these helicoids. And somebody was asking me yesterday about in what sense was this adding, or how am I adding these together? If you like, really, this whole program, let's see if I can find the thing I want to find. I'm sure I can. This whole program of drawing surfaces like so, and saying that this triply periodic minimal, this periodic minimal surface, Riemann's minimal surface, can be written as a height function. So here's z, like so, that's z. Really, in a sense, what we're doing is we're finding complex functions that have the minimal surface as their Riemann surface, right? So we construct meromorphic functions whose minimal surface, whose Riemann surface is this one, for instance. Here, right, you take this function here, or actually, let me keep going. You take this function, right? So you have log of the Jacobi elliptic function evaluated at these funny values, where k is the elliptic gnome. And you look at that function and you say, oh, what's its Riemann surface? And this picture here is its Riemann surface. So now, in a way, this is using the Riemann surface, which was only a topological thing in a certain sense. We're actually using the Riemann surface as a geometric thing now by actually embedding it in the third dimension. So that's sort of the program there, and how it is that you can add things together, because each of these corresponds to a branch cut in the complex plane below. Right, so these are just branch cuts. So let me now switch to the different topic, the other topic, the Diblock copolymer topic. So Diblock copolymers have a very rich and long history, and are related, and are some of the best examples in nature of minimal surfaces, in particular the triply periodic ones. So what's the idea in a Diblock? In a Diblock copolymer, so it's a, oops, did it again, see? Someday, right? So here we go. A Diblock, it's a Diblock because there are two blocks. There's the red block and the blue block. If you don't want to call them red and blue, you can call them polyethylene and polystyrene. All right, that's probably what they really are. They're two polymers. And they're copolymers because there's two polymers here, two of them, that are glued together in a covalent bond. And the only thing that's really important to know about Diblocks is red hates blue. Red hates blue, blue hates red. And because they dislike each other, they don't like the fact that they're bound together. They're handcuffed together at this point. And so what they do is they form very complex phases. Sorry. They form complex phases. Is it coming? Yeah. Hold on one second. I see what the problem is. I'm just going to show it to you this way, right? They form these complex phases where, one second. I can fix this. I'm sorry. So they form these complex phases where they try to separate. So for instance, in some ways, the simplest one is again, remember it's morning for me here. Okay. So they form the simplest phase here where you have equal amounts of red and blue. And what they do is they just form these layers. And the way that by making layers, they minimize the interface. See how minimal surfaces come up right away? What they do is you have red on one side and blue on the other side. Sorry, blue on the other side, like so. Blue, blue, red. And since the red and the blue dislike each other chemically, they try to find a surface that separates them that has the smallest area. And so they naturally like to have minimal surfaces. What's strange though is, or the other part is that to do this, you have to distort the polymers. And so here it's quite easy. The polymers are just stretched a little bit. They're stretched in this direction and that direction. But imagine instead that you have a situation where you have a very small amount of red. So you have a Diblock that looks like this. It's a very short red chain attached to a very long blue chain. And so if everything were great, the blue chains would just ignore the red chains altogether and they would just fill space with blue, right? You would just have a sea of blue. But what happens is because there are red chains in there and the red chains really dislike the blue chains, they find other red chains and they make little droplets of red inside, right? And these little droplets of red are surrounded in an ocean of blue. And so what you should imagine is that between these red dots here, between these red dots, it's all blue polymer. And it makes a sphere because a sphere minimizes the interfacial area for a fixed volume of red polymer. And then finally, these spheres, in an attempt to minimize the distortion of blue, they organize themselves into a periodic lattice. And then what happens is you go to a state where now the red block is a little longer. It's not a lot longer, but it's a little longer compared to the blue. And instead, it decides that the way to minimize the surface area, the interfacial area, and minimize the distortions of the blue polymers is instead of making little spherical droplets, it makes cylinders. So there's a bunch of cylinders. Right? If I looked at it from the top, I would see a plane with red cylinders packing nicely, like so, with blue everywhere else. So if you like, this is sort of a two-dimensional structure. This is sort of a 2D structure that's then extended in the third direction. This is a real three-dimensional structure. And on the other side, you have exactly the mirror phases, where here, for instance, you have a very short blue chain attached to a very, very long red chain, and so forth. So it's symmetric. And then in between, you have the most exotic of all things. You actually have a bicontinuous network. So what happens is these red cylinders, or the red cylinders here, the red cylinders, instead of just becoming plain red cylinders, they actually become branch structures, pairs of pants, like so. And they make a complex network of tubes in an ocean of blue. And this complex network is actually interesting from our point of view. So remember, I showed you that you can build a structure like this, Shirk's first surface, out of individual helicoids, like so. And you can then assemble them into a whole structure like this, where you have a domain, where you have a bunch of layers like this. So that was that lamellar phase, the red and the blue. I'm sorry. Right? So you have, in each of these regions here, you have stripes of blue and stripes of red. And then maybe there's some sort of boundary condition. And what happens is that between this set of lamellae and this set of lamellae, there's a twist. And so you actually then end up seeing structures that are just like this minimal surface. And so now you have the next region over, where the lamellae are rotated compared to the old one. And you can accommodate that. I showed you yesterday how you can accommodate a set of layers with one normal, like so, and a set of layers with another normal, like so. You can accommodate them with Shirk's first surface. And you can do that smoothly, so that instead of having a place where you have to cut the whole domain, instead, you just have these helicoids. Each of these black lines is a helicoid. And, this is a 35-year-old, 34-year-old subject, and you can look down here to see more about that. But this isn't just something that theorists talk about. You can actually see these structures. So I'd like you to, your attention, pay attention to this structure here, the picture here. This is real experiment. This is some material that makes layers. You see the layers? Like so. So here are the layers. And what in this experiment, you have the situation where you have a box. Here's the sample. Like so. And you're looking down from the top. Here's your eye. Looking down from the top. And on the top surface, you have a bunch of layers. And then as you go down, you have a new set of layers, but these new set of layers are rotated compared to the first set. So A and C are two regions where there are layers. And then E is another region where there's layers. So you can see as you go down, the layers are rotating clockwise. But I think it's very beautiful that you can see in region B, you can see the interface between the two. And if you think about what this is Shirk's surface. See, you can see the back part where one set of layers is like this. And you can see the front part where a different set of the layers are like this. And in between, you see these lines. Those lines are exactly helicoids. See, look at them carefully. The helicoids, as you go around them, let's see if we can do this. As you go around them, so you come this way and then you go up, over, up, over, up, over. So you're actually going and rotating around that line. And so here's physical example, a physical realization of the helicoids and Shirk's first surface, all in this quite simple system. And here you can see, using microscopy, electron microscope, you can actually see regions of this in the Diblocks. These are Diblocks. And you can see, to me, at least you can see, here you go, here's a black region, and then it attaches to this black region, which attaches to that black region, that black region. And what's happening as you go around this line, the layers are rotating around that line. And here you can see this stippled pattern, which is the same stippled pattern you see here. And this is a grain boundary. This is a Shirk surface. And, you know, these things happen and have been happening in crystallography for ages. It was really people like Ned Thomas who had this, this vision that you could think of these in terms of minimal surfaces, or that it was valuable to think of these in terms of minimal surfaces. And so what I want to talk to you now about is the last topic, is the gyroid. And yesterday, Dr. Day said, oh, well, don't these surfaces come up all the time in electronic theory and in crystals? And they do. So this is the gyroid. And it's hard to get your head around it. But what you have is you have this network of blue tubes, like so, like I showed you before. The blue tubes branch. There's a twist between the two branches. So you can see that here. There's this node, and they're rotated with respect to each other. And then you have two interpenetrating networks of blue polymer, right, that are passing through each other, like so. And inside, in between, it's all red polymer, red. And if you look at the interface, the boundary that separates this blue network from this blue network, this is the surface that divides it. So on one side, I'm pointing, but you can't see it. On one side of the surface, you have one blue network. And on the other side of the surface, you have the other blue network. So it's kind of like the knitting. You have these two networks that never touch each other because they're separated by the red network, or by the red polymer, because the blue and the red polymers are attached. And there's a surface that divides them in two, just like with the knitting. And it's this surface, and it's called the gyroid. And here, the gyroid continues into three-dimensional space. It gets quite complicated. And these are pieces of the gyroid. Oh, and I see. And you can see here, if you go, oh man, if you go forward, if you go to this picture down here, what this is, and I know this is supposed to be a conference on zero mean curvature surfaces, but you know what you can do is you can take the zero mean curvature surface and you can evolve it normal to itself. And when you evolve it normal to itself, it becomes a constant mean curvature surface. And if you evolve the gyroid normal to itself, you end up with these sets of tubes, the very sets of tubes that I was talking about. So you can either start with the tubes and find the surface between them, or you can start with the surface and you can push off the surface normal to it, you can evolve it, and you get the tubes. And this is just a recap of what the Diblocks do. And this is the phase we're going to study. Now, I promised yesterday, or I mentioned yesterday, promise is too strong, that generically you imagine getting these triply periodic minimal surfaces in a large variety of systems. So I have a theorem. It's not really a theorem in the mathematical sense, and it's not really a proof in the mathematical sense, but it's a statement. It's a lore statement, right? That minimal surfaces are generic. in phase separated materials. So let me set the problem up. You have two phases. Maybe you have red and blue. You have the red phase, and you have the blue phase, like so. And you describe everything simply in terms of some phase field, phi. Phi, did it again. And now it's going to be all gone. Yeah, sorry. Right? So you have red, you have blue, like so. And you have this phase field phi. Phi is equal to 0 if it's all red. Sorry. Phi is equal to -1 if it's all red, and +1 if it's all blue. All right, so phi lives in the space -1, 1. Like so. And then you write down some sort of energy. You write down some sort of free energy, functional, that describes this material. And so what do? You write down some energy, some objective functions that you want to minimize. And you say, well, there's a bunch of terms. So I integrate over space, like so. And there's one term, which has some coefficient in front of it. I'll call it k, which says phi likes to be constant. So I write the gradient of phi squared. Why is this a good term? Why should I have that? Because red likes red, and blue likes blue. So if you have a region of space, right? So here's your box. Here's your box. And you have a region of space with red. Well, the region of space next to it also like to be red. Certainly doesn't want to be blue. And so you have some energy cost associated with changes in phi. In other words, if you have an interface between red and blue, then this costs energy. You also have something in the energy that tells you, oh, there's some potential that depends on phi. Maybe it says, oh, I like phi. This is some potential. For instance, it could be a potential like this, which is lambda times 1 minus phi squared squared. And so what does this do? This has two minima. Two minima at phi is plus or minus 1. And there's an energy cost. If it's not pure red, then you've mixed in some blue with the red, and it doesn't like that either. So this tells you where the minima are. And together, these things lead to phase separation. Now imagine that you have a situation where the system is symmetric. Assume symmetry between red and blue. And what that means is that you have an exact symmetry. Phi goes to minus phi is a symmetry of F. So if you took all the red region and replaced it with all blue and vice versa, you would get the same thing back. So let's just think about that. For this to be true, right, this implies that V of phi is V of minus phi. And so writing down my energy again, trying to write down my energy again. I have F is the integral over space of K grad phi squared. Notice that this automatically has phi goes to minus phi symmetry, plus V of phi, like so. And let me imagine the Euler-Lagrange equations. Remember, I'm allowed to use them because I showed their picture yesterday. Euler-Lagrange gives me minus k del squared phi plus v prime of phi equals 0. So what? Well, v of phi is even. So v prime of phi is odd. And that means that v prime at 0 is 0. And why is 0 interesting? Because phi equals 0 is the surface which divides blue from red. Right? So you imagine you have this surface. Over here, it's very red. Over here, it's very blue. And in between is the place where phi is exactly 0, because here phi is +1 and here phi is -1. And phi equals 0 is the surface that divides blue from red. And if that's true, it means that phi equals 0. On the surface, phi equals 0. Del squared phi is 0 because of this. And now, one last bit. Imagine I look at, say, the magnitude of the gradient of phi. So the gradient of phi has some value, it has some magnitude, but this is a symmetric function. This is symmetric. This thing is symmetric around phi equals 0 because the two phases are symmetric. Blue and red can be interchanged. If I switch blue to red and red to blue, everything's exactly the same, which means that the profile is the same on both sides. So the magnitude of grad phi is the same on both sides, which means grad phi is an even function around that surface. And you say, okay, what's that give me? Let me calculate for you the divergence of grad phi over the magnitude of grad phi. That's Laplacian phi over the magnitude plus the Laplacian phi dotted into the gradient of 1 over the magnitude. Well, this term is 0 on phi equals 0. And this term is 0 on phi equals 0. Because the gradient, the magnitude of the gradient of phi is symmetric, so its gradient perpendicular to the surface, right? Because this is perpendicular to the surface. Its gradient perpendicular to the surface is 0 because its gradient is an odd function since it's an even function. And so what's neat about this is I've just shown you that this has to be 0 on the green surface, which is the surface that divides the two regions. And this is nothing more and nothing less than the unit normal to the surface. And so again, I've just shown you that the divergence of n equals 0 on phi equals 0 surface, which means that the green surface is a minimal surface. And so it's generic. It's a generic property. In fact, I could add even higher order terms here. I could, if I wanted to, add grad phi to the 4th and grad phi to the 6th. Terms which still dislike places where red and blue are in contact with each other. They try to make the things constant in space. And this argument would still follow through. I would just have more terms here, which are even higher gradients of phi, but would imply that Laplacian of phi is 0 on there. So this is a generic thing. You can certainly cook up models where it's not true, but generically you expect to have these minimal surfaces as the interfaces between two regions that are symmetric. Okay. So here's the gyroid. All right, I want to go back to the gyroid, tell you about, oh wait, is there something in the chat? Oh, yeah, it's okay. I'm good. So let me remind you or tell you some amazing things about the gyroid. The gyroid was, I told you, discovered by Alan Schoen in the late 1960s as this intermediate state between the P surface and the D surface. So it's a bonnet transformation at some funny angle. And the P surface is a cubic surface. It has a cubic symmetry. So you have these nodes. Right, these are the little handles. Let's see if we can find a picture of it. Remind you and to remind me what they look like. Here we go. Right, so when you look at these guys, I'm sorry. When you look at these guys, each of these nodules here has six holes all coming together at the central point. There's a network, the skeleton, which is a cubic skeleton. The diamond has networks where you have four coming together, and that's a fourfold skeleton. And the gyroid has one where it's threefold. And so here's a picture of it. And you can see that if I draw the networks, so this is the surface, and here are the networks. And there's a blue network and a red network, and maybe you can see each node on the network is threefold coordinated, right? So there's three edges coming out of each node, like so. And this red network and this blue network are interpenetrating networks that are separated by this surface. So if I drew the surface that was in between the red network and the blue network, I would get this gyroid. And if the two networks are identical in every other way, then what do you expect? If the networks are identical in every other way, you expect that this surface that separates them will be a minimal surface based on my argument. And that's exactly what happens, right? So you have this material. Remember, you have the Diblocks. What is the red network actually made out of? The red network is tubes of blue. I know this is confusing because I use blue and red in two different ways. And the blue network is also tubes of blue. And in between the tubes of blue, there's an ocean of red. Which you can see right here, right? Or here, this is tubes of red and an ocean of blue. So I said it backwards, right? So here are tubes of red. In a blue ocean. So you have these red polymers, right? These red polymers in here. They are forming this network, like so. And there's two of those networks, and they're interpenetrating. And both networks are described. One network is the red network on this right-hand picture, and the other network is the blue network. In other words, this picture I keep showing you is just wrong. Okay, really, I should say those are all the same color network, and they're separated by this interface. And my dumb proof, my lore proof is that interface will be a minimal surface. And that minimal surface is the gyroid. Now, I'm going to, in this last bit of the talks, I'm going to tell you about some research.
Can I ask a quick question?
Oh, please do.
Yeah,
Yes.
so how do you know it's a gyroid? Sorry, I think the vertex calculation.
How do I know it's a gyroid, or how do the experimentalists know it's a gyroid because they look at cross sections of it. They look at electron micrographs and they look at cross sections, and from it they build up the three-dimensional structure. So they can do, it's kind of a neat thing they do. We would call it just tomography. It's what they call it too. They take the real material and they take slices and they look at each slice under a microscope, and then they reconstruct the whole thing and say, this is what it looks like in 3D.
I see. Okay. So
Okay,
experimentally it has been seen.
experimentally it's been seen. And experimentally it's very difficult when you look at pictures to distinguish, say, the gyroid from the diamond phase, but careful experiment has shown it's the gyroid phase. And you can do other things like neutron scattering. You can do this in Fourier space too by doing neutron scattering and so forth. So there's been a lot of work, and I'm about to show you some unpublished work we've done. I want to come back to this slide in a second. I'm going to address your question instead, which is, here is data. So this is real data, right? My student Suman, she calls it the mac and cheese, right? So here's data. The dark, the yellow part, the bright yellow part is this polymer, PDMS, whatever PDMS stands for, polydimethyls. I'll make that up. I'm sure it's dimethyl something, silicon probably, or silicate or something like that. And the other side is polystyrene. So the dark regions are polystyrene and the bright regions are PDMS. And you can see, you asked this, right, Rukmini?
Yeah, once again, sorry.
Yeah, you asked the question, right? So this is it.
Yes,
This is how
yes,
they
yes. That's right.
reconstructed. Yeah, so here, this is a 3D reconstruction of actual data. And it's quite messy. It doesn't look so beautiful like a gyroid. And in fact, and this is data from Ned Thomas. What they do is they build the skeleton. So they say, oh, what does the network look like that is separate, right? So they go back. They say, okay, there's a network of PDMS and there's a network of polystyrene. And now we reconstruct where the network is. And here's the network. And this is the network of one of them. Maybe it's the network of the polystyrene or the PDMS. It doesn't matter. This is what it looks like on the top. This is a side view. So they can actually reconstruct the center lines, the locations of the maximum density of the minority block here. And then we can look at it and we can say, well, this is an interesting network. What does it look like? Right? How do we characterize this network? And remember, the gyroid is very special because the gyroid is a system where the network is threefold coordinated. And Suman has calculated where the coordination of the networks. And you can see that most of the networks, most of the nodes are colored red, which means they're threefold. They have three edges coming into them. But some of them are fourfold. Some of them are even twofold and fivefold. And what's crazy about that is you can see there's a clear separation. There's a clear separation where in this region here, it's pretty much ordered. You have a threefold coordinated network. And this region here, it's kind of disordered. And what's happening? In the region over here, there are two networks. Two interpenetrating networks. With threefold coordination. That's in this region here. And here, to our surprise, there's really only one network. The two independent networks have combined themselves into one network. And I guess they've done it by using these fourfold junctions, but we don't really understand exactly how. So let me try to say what's weird here. So on the left, on the upper left, there's a surface that divides two networks. And it's the gyroid. On this side, there's only one network. So there's no dividing surface. What is it dividing? So what happens? How do I go from a place where I can say there's a surface that's dividing a network to saying that there's a surface that doesn't divide the network? Or sorry, there is no surface because there's only one network. What's happening as you go across this line? How do I even imagine that? And there's a very brilliant crystal physicist, Pavel Peronsky. And Pavel asked this question a long time ago. He said, oh, here I have a picture of the gyroid. Sorry, it's not the gyroid. A picture of the P surface. Right? So it's that surface like this where you have these six-fold junctions and you just keep attaching them together. And this is a spherical region of the P surface. And Pavel asks this question. What happens if you take the surface and you make a cut in the surface and then you glue it back together? So watch that again. All right, you cut the surface. Come on, surface cut. You cut the surface and then you glue it back together. And since the inside is just like the outside, since the surface has this symmetry, you can glue it back together, and there's only a place right here in the middle where it's a little funny looking, in particular here. It has some kind of funny belly button. But the rest of it is perfectly fine. If you were just drawing a surface, you wouldn't have a problem. But this is weird because this new surface that he constructed connects the blue side to the yellow side. Up until now, I've always been talking about these surfaces as being oriented objects that separate space into two volumes. But now, just by adding this funny region in the middle, Pavel's constructed a surface that actually only has one side. So this is a Klein surface or a Mobius kind of surface. There's only one side, right? The two volumes are connected to each other. And so what we thought was interesting, and this is still work in progress, but I thought I'd tell you about it, is this material here is exactly doing that, right? So here is a situation where up here, I have a surface that's oriented, and it must be on this side that it's non-oriented. Because there's only one side, there's only one network. So how do you go? What's the transition look like? So here we're using experiment because we have data to try to visualize how real surfaces do this, constrained by energetics. But those energetics, as I've argued, frequently force you to want to have these minimal surfaces. And so this is what Suman did. So just to make it easier, I'm drawing blue and red again. The networks are all the same. The blue network and the red network are made of the same material. And if you look at a perfect gyroid, in a perfect gyroid, what you discover is that this is a perfect gyroid. In a perfect gyroid, there are closed loops. They're 10 edges long. In order to come back to where you started in this gyroid network, you have to take a path of length 10. And as you go around that path of length 10, this closed loop, this is one network. The other network is interleaved between it, and this is the other network. And the other network also has loops that go around, and they're linked. So what she studied is she studied the linking number. She studied, if you look at one green loop in one of the networks, you fix this one, how many of the loops from the other network pierce it? What is its linking number, or how many links are there? And she calculated that. And there are 10 different ways that they can link. So in a perfect gyroid network, in a perfect gyroid, where there's a surface that divides the red network from the blue network. That's why they say it's sometimes double. They say, well, there's the blue network and there's the red network. There's two networks, and those two networks are divided by a gyroid. Here are the 10 different ways, or the 10 different loops of one network that go through the same red path of 10. Right, so the red, she calls it a bottle, right? The red bottle shape has 10 of the other network loops piercing through it. That's in a perfect gyroid. So this is a way of measuring how gyroid is your gyroid, right? If every loop has 10 loops going through it, then it's like a gyroid. If suddenly you find a place where through one of these loops you have fewer or more loops, then it's not much of a gyroid there. So what we're trying to do is we're trying to use topological measures. Topological measures are robust to noisy data. And so we're trying to discover what the interface looks like by studying this. And so here's what Suman did. She looked at the loops that were length 10, and the loops that were length 9, and the loops that were length 8, and so forth. And you can see that in this region, in the ordered region, it's the same ordered region. In the ordered region, you don't have loops of any length except for 10. In the disordered region, oh, you can't see that color. In the disordered region, here and here and here and here and here and here, you get loops of all sorts of lengths. So you can see that something is happening. In the disordered region, you don't have to take 10 steps to get back to where you started. You can take only 8 steps, or 7 steps, or 6 steps, sometimes even 5 steps. So you have much shorter loops now, which is somehow saying that one of the two networks have hooked onto each other and made shortcuts and short circuits to go from one to the other. Then she looked at the linking and she said, okay, here I look at all the loops of length 10. So I look at all these bubbles like so. So she looked at the bottles and she said, how many of the bottles have 10 loops going through them? 10 loops would mean that she would color them blue. And if they had, say, 7 loops, she'd color them green. And she discovered that, that most of the time, the ones that were linked were up in the ordered region. And here, in the disordered region, look at that. It was mainly 0. Most of the time, those loops had nothing linked in them. So on one hand, on the upper left, you have a bicontinuous network. You have 2 interpenetrating networks separated by a surface. And on the right, you have only one network. And that network isn't separated by anything, or if it is, we don't know what it is. So somewhere there's a transition between these two. There's a transition from a oriented to disoriented surface. or to non-oriented. And I know that, at least it's my experience, that most of the time when people study zero mean curvature surfaces, minimal surfaces in general, that they're usually studying ones that are oriented. And here I'm trying to make the case that non-oriented ones could also be quite interesting, or they can be non-oriented almost everywhere. And then somewhere they're not actually a minimal surface, or there's something that isn't quite a surface. There's some singularity. So you may say in most of the space, it's a non-oriented surface, a non-oriented minimal surface. And then there's some places in the middle where it's all messed up. And in the messed up regions, you can't say it's a surface at all. There's some kind of defect. But that would be interesting. Those defects are the things that we can study and look at in real experiments. I'm just going to end by telling you some other topological measures that Suman has calculated. She looked at the persistent homology. And, oh, there's a question?
Yes, yes.
Excellent.
Can you go back to the previous slide, please? Yes.
This one. Yes.
Yes. So by looking at the distribution of loops of various lengths, can
Yes.
one predict the cuts, where the cuts have to be made, so that you get this surface?
Okay, so the answer is yes, but for this data set, the answer is no. This data set, we have a better data set that we're working on which we're working now. This data set is weird and skinny. I'm not saying anything is weird about being skinny. I'm just saying it's very not three-dimensional. Right? It's a very thin slab. It's a thin slab. And so the problem is that most of our data is dominated by surface effects. Right? And so, for instance, nobody shouted about this, but when I was calculating the coordination number, or when Suman calculated it, she found some places where there were only two edges coming out of a node. How can you have two edges coming out of a node? Right? That doesn't mean anything. What that really means is that there's a third edge, but it's sticking out of the surface, but we're not tracking it. So we are working now on better three-dimensional data that we also got from Ned Thomas. And that is our hope, to do exactly what you said, to reconstruct it. And let me hold on. Let me go back to where I was. So one of the things that we're trying to do to at least characterize it, so here's the program. This is all work in progress. Here's the program. 1, we need to find the disordered and ordered regions. And if I go back to the picture I showed you of the data, the mac and cheese, it's hard to tell exactly what's ordered and what's disordered in the mac and cheese. So we want to have some quantitative way of deciding where it's ordered and disordered. And so Suman's been developing these topological measures. Do it by the linking number? Can we do it by persistent homology? Can we do it by the average length of by the length of the loops? Once we have that, we can go back to the rest of our program. Once we can find that, then we can find the interface. And once we have the interface, we'll reconstruct it. So then we'll see exactly what it is that you want to see. If you send me your email, I'll send you you'll be the 5th person to know after our group.
Thanks.
Sure. So let me just remind you a little bit about persistent homology. What's the idea in persistent homology? In persistent homology, you imagine that you have a bunch of points. So I always like to think of the letter C. So this is, I start with the letter C. And then I take data from the letter C. So I sample the letter C, and I get these 5 points. So this is the sample. It was a random sample. I got these 5 points. And you say, well, that just looks like 5 points. And I say, you're right. It looks just like 5 points. And if I think of this topologically, I'd say, oh, this is five independent things. I would say that it's the 0th Betty number is 5 because there are 5 independent domains. The first Betty number is 0. The second Betty number is 0. There aren't any closed loops. There aren't any closed surfaces, and so forth. But then in persistent homology, the axes here are measuring something. These numbers are measuring something. They're saying, oh, instead of thinking of these as 5 points, I'm going to grow the points. So I'm going to take these points and I'm going to grow them. And so as I grow those points into little disks, I still have B0 is 5. There are still 5 independent regions. But at some point, these purple regions start to overlap. And suddenly, B0 is now 1. I only have 1 domain. So what happens is, you can see it here, something is born, right? You have a certain number of things. And then at some height, at some place, when the radius of the disk get big enough, they all die. 4 die. And this is the death of 4 of them in this particular picture. And then as they get bigger still, you can imagine a situation where you get something that's filled in, but it still has a hole. There's a hole in the middle. And so suddenly at that point, B1 becomes 1. So suddenly there's a birth. There's a birth of a closed loop. And then, as they get bigger still, they fill in the hole. And B1 goes back to 0 because there's no closed loops anymore. And that's the death. So you see, you can count. Here, what's this guy here? This guy here, that's the 1 domain that lives the whole time. Here is the birth and death of some of the domains. Here is the birth and death of the closed loop. And instead of doing it for my simple letter C, Suman did it for the whole gyroid network. And in a perfect gyroid network, you have individual points. Let's erase all this. Like so. In the perfect gyroid network, what do you have? You have the birth of some points. So here, 1 point is born. That's the point that lives forever. That's the whole data. And you have the birth of a bunch of other points, like so. And then, eventually, when you make them bigger, still, they die. So this thing dies. These are the ones where you had your network, and you were drawing your network as isolated points, and then suddenly the points get big enough that you start to have a network, like so. And look, this guy dies at exactly the same place that this set of loops is born, right? So at 0.38 or whatever, a bunch of points die and a bunch of loops are born. So this is a place where now, these individual points are forming closed loops. And so you can see the birth of the network. And then at an even larger radius, as these get thicker, there must be 2 networks that join into one network. And so that's some network dies, this dies, and there's a new birth, and the networks are born. And so this is sort of a way of trying to characterize topology, but also having some geometry in it. And this is what would happen for the perfect gyroid. This is for the perfect gyroid. And then Suman started studying it for the data. And in the ordered part, you can see that it's not very different. You have birth and death here, roughly at the time that you have death, at the death time here, roughly is the same time that you have the birth of these loops, and then they die. And there's even the birth of some volumes. So sometimes you have a bunch of points in 3 dimensions, and they clog themselves up, and they actually make not a handle, but actually a volume, a closed cell. And the important thing about persistent homology, and why it's interesting at all, is that Edelsbrunner, when he developed it, proved that and others proved that as you continuously deform the data set, it continuously deforms this this birth and death network, this birth and death picture. So there's nothing that's going to happen discontinuous. And so you can see that this picture here, these two things are continuous deformations of each other. And this is one of the two networks, one network, and this is the other. And so you're all going to say, okay, this is in the ordered state. What about in the disordered state? And in the disordered state, it's totally different. Here's the imperfect region. This is the disordered region. In the disordered region, right? See, when you look at persistent homology graphs, you say, oh, what are the interesting things? The interesting things are the things that are very far away from the diagonal. Why is that? Because those are things that are born and die, but they live for a long time. So these are places, these are saying, oh, well, there's a bunch of points that actually live for a long time. So you can think of them as points. And this is telling you that there's a bunch of loops that are actually quite long-lived. So this means you have high confidence that the sample has loops. But look, in the disordered region, you got nothing. These are very short-lived. So whether they're actually loops or they're just distortions or noise from the data that makes it look like there's loops, we're still trying to determine. But you can definitely see in the disordered region, you'd be hard-pressed to say that you would really characterize this as a bunch of loops. It may just be a giant big blob. And so that's where we're at. Suman is furiously working. I should add, Suman's from Bangalore. She grew up there. So she would love to come visit if you guys ever had an opportunity to invite her. And what this is saying somehow is that the ordered region really looks like two networks. But the disordered region, what does it have that's long-lived? The disordered region has cells that seem to be long-lived. And so it may be that in the disordered region, it's much more reasonable to think of this network as developing a bunch of faces. So that instead of thinking of it as two networks, you actually should think of it as some sort of set of three-dimensional cells or two-dimensional cells bounding three-dimensional space. And so, again, we don't have the answer. We don't know. How do you go from something that looks like this, a minimal surface that separates two regions, to a non-minimal surface? So we are exactly in the middle of that program now. And I hope I can report more to you in the near future. And I think that's a good place to end. I was just going to say that these minimal surfaces, these come up in other liquid crystal systems, and you can construct surfaces that have this symmetry, and they actually exist also. So Dr. Day was asking me, how do you see it? Well, you can actually do experiments where you see regions. What is this? This is the outside is a minimal surface. And then you grow normal to the minimal surface. So each of these is a CMC surface. And then you can actually observe the CMC surfaces in the material when you look at them under a microscope. So this use of minimal surfaces as a modeling tool is very good because of that Lor theorem, that meta theorem that I proved to you, that minimal surfaces typically divide symmetric regions in half in physical systems. And I think, let me see where I am. Hold on. I think this would be a good place. I'd really like to end here with what will our data show? So I hope to be able to tell you that there's some mathematical interesting thing that happens when you go from a space dividing minimal surface to something that's more like a foam. How do you connect those two things together? How do those networks interpenetrate? It would be finally answering the question or validating the idea that Pavel had of making these Mobius surfaces or Klein surfaces where you've connected two regions together. And the interesting part would be, what do these belly buttons here look like? What do these funny regions look like? Those would be the regions that divide space over here, which kind of looks like a bicontinuous region, to a region here where it's not bicontinuous anymore, where there's only one side of the surface. So I'll leave you with that, and send me your email if you want to be the first to know or the fifth to know what's happening. And I'm happy to take any questions.
Thank you very much for this very interesting and intriguing talk. Yeah, any questions?
Yes. Right. So your meta theorem, where you say that minimal surfaces typically appear as a boundary of two regions which are symmetric. So similarly, do you have a meta theorem for other CMC surfaces where curvature depends on the non-symmetry, or what is the fraction? I think your first example was.
I don't have a meta theorem that I love as much as that meta theorem, which I really should attribute to Robert Hollish, right? But let me remind you that I showed you yesterday, right, that minimizing the interface, minimizing the area, the surface tension area, and the volume, right? So this is the energy that soap bubbles want to have, right? So they want to minimize the interfacial area, and they have a fixed volume. You discover the Young-Laplace law that the pressure is equal to 2 times the surface tension times the mean curvature. This said to me that if you have two regions on either side, two bubbles that have exactly the same pressure, then the interface between them is going to be a zero mean curvature surface. And if you have two bubbles which are of different pressure, then you'll get a mean curvature that isn't zero. And so then I'd say, oh, well, when they're the same pressure, then they're the same. That's a meta theorem, right? That two regions that are exactly the same means that there's no pressure difference between them because they're identical. One doesn't want to seep into the other region. And if you try to do the same thing for a CMC surface, then I would make some argument that you have two regions, and if it's not that the pressures are this different, then you can say their chemical potentials are different, right? So you could say, I could redo this whole thing and talk about the chemical potential of two materials, right? Or some other thermodynamic quantity and talk about the interface between them. But no, I don't have a theorem that's as clean as the other one. Not yet, but you could prove one.
In particular, your blue and red molecule example, Can we go to that slide where you show in the sea of blue, if there are fraction of red present, then they will form various shapes depending on the fraction. So
That's correct. And
yes.
so let's be really clear about this. This is special. Here, in this system here, in the gyroid network, it's two red networks, two independent red networks separated by a sea of blue. So the two sides really are symmetric. There's a red network on one side and another red network on the other side. So they truly are symmetric. Right? Here, this was a situation where phi is 1 on one side, and then it becomes -1 on the other side. Right? These are even more exotic. These gyroid networks are more exotic because phi equals +1 and phi equals -1 are the same. They're actually physically the same thing. Right? And that's what's different, right? These really, my theorem should be even more strong for these guys, or my pseudo theorem, right? For the gyroid ones, because there you have two networks that really are exactly identical, and everything should be symmetric. Here, you could say, well, maybe the red interface and the red region, the blue region, maybe the magnitude of the gradient phi doesn't have to be symmetric. Maybe they're not really symmetric. They just divide themselves up into red regions and blue regions. But if I look at it chemically, they're not symmetric. Here, they really are symmetric. Symmetric by I don't know what to say. They're symmetric. These are kind of symmetric. These have red-blue symmetry, sort of. Is that what you were getting at?
Yes, I understand that. But if you focus on one of the sides, okay, so as you, let's say, decrease a fraction,
Oh, yes.
see change in the topology, right?
Right, and you're right. These are CMC surfaces.
Okay.
So divide.
Right. So I guess there is a continuous modeling of that where there is a transition from one type of CMC surface into the other.
I would love if that were the case. That would be how a theorist would love to see the world. Unfortunately, that's not how they can't do an experiment where they change the length of the red and the blue. All they can do in an experiment is they can prepare different samples, right? It'd be so cool if I could make a knob and I could, at that moment, tune it and turn the knob and have it go from one to the other and watch that happen, right? And so the next best thing that we have is what I showed you, is that we can at least look at data where you have ordered regions next to disordered regions. And you can hope that that is some window into exactly what you're talking about.
Okay. Yeah, it was very exciting to see this. Thank you.
Thank you.
Any other questions?
Who sent me an email this morning? Raise your hand. Oh, okay. Hi. Okay, good. I will get back to you then.
That is Dheeraj. Okay, if there are no other questions, let's thank Professor Kamien again for this very interesting talk. And